Good morning, good afternoon, and good evening. Welcome to AI for Good. My name is Bastian Kwast from ITU, the International Telecommunication Union, and it's my privilege to introduce a session today, Adversarial Attacks and Defenses, with Professor Aleksander Madry from MIT. ITU is the United Nations Specialized Agency for Information and Communication Technologies, and is also the organizer of AI for Good, together with 38 UN sister agencies, ACM, and co-convened with Switzerland. We're using the Q&A functionality to create an engaging discussion that you can find at the bottom of your screen today. Additionally, there's also the chat functionality that you can use to communicate with other participants. Please make sure that you set the recipient to all panelists and attendees. And with that, it is now time for me to hand it over to Wojciech, our host of the Trustworthy AI series. Hi, Wojciech.
Yeah, hi. So yeah, it's a great pleasure and a great honor for me to introduce our speaker today, Aleksander Madry. He is one of the experts in adversarial defenses and adversarial attacks. And he is a professor at MIT, professor of computer science, and a member of CSAIL and the Theory of Computing group, and also the director of the MIT Center for Deployable Machine Learning and the faculty lead of CSAIL Trustworthy and Robust AI collaboration. So he has received many awards, best paper awards, and have published at the best conferences in our community. So it's a great honor, and I'm looking forward to the talk. And yeah, what's to your opinion about how much can we trust AI in the future, and how robust can we make it? So welcome.
Great. Thank you, Wojciech, for the kind introduction, and thank you for inviting me here. So let me just get my slides going, and we will be good to go. So yes, much of my work is about exactly thinking about machine learning, and in particular, all the things that can go wrong when we deploy machine learning systems in the real world settings. So yeah, so that's what I want to talk about. But like what I want to do today is not necessarily tell you all the things that can go wrong and all the solutions for trying to counteract it. I actually want to tell you a little bit more about underpinnings of all of this, like kind of where all of this is really coming from. Okay, and then I'm happy to expand on these questions in the Q&A session. Okay, so essentially I want to tell you a little bit about why do machine learning models fail. And yes, so the reason why we are here is that clearly machine learning is a success story. Okay, so it all has started in some way by the success of on the Imagenet, where Alexnet kind of essentially made suddenly like a lot of progress, and kind of since then we just see this explosion of all the applications of machine learning in general and deep learning in particular. And currently, like machine learning is deployed in, or at least people are thinking of deploying it in just about every aspect of our lives. Okay, and in particular, if you think about AI for good, well, yeah, that's what we are trying to figure out. That like as we are when we are deploying these models, we would like to do it in the right way. So as you can imagine, I'm giving a lot of talks about machine learning, and of course, like the question that I often being asked is saying, okay, so we have this exciting technology, all this excitement, all these things that we could not have, 15 years ago sounded like science fiction. Now we seem to be able to do. So the question is like, are we there yet? Okay, so maybe like, is all that left to do is just to polish and scale up the things we have, and and then we will be ready, at this point will be the smooth sailing. Okay, so kind of the question sort of asks, okay, so if you think about what will we need for like responsible deployment of machine learning, well, the first thing you realize, you need is clearly the performance. Like this using these ML systems needs to provide a positive value. And yeah, that's, I would say we have, yes, like kind of like this machine learning systems seem to provide value. They seem to be providing performance. But then we realize that, okay, that's clearly a prerequisite, but that's not the only thing we need. What we also need is robustness. So we should be able to use this machine learning on the data that was unvetted or is untrusted. That's kind of the adversarial aspect, but also this complementary aspect of reliability. We kind of would like to, so every machine learning system can fail for many reasons, but at least what you would like to happen is that it fails in a what I would call a graceful manner. Okay, and that's kind of what I would call reliability. And finally, the third aspect that is often raised is this question of interpretability or explainability. Essentially, we would like this ML to be kind of possible for us to to understand why the model made decisions it did, both because this is a way to get some quality assurance, but also for regulatory reasons. Kind of that might be very important. Okay, so these are kind of the three aspects. And again, the question is, do we have that already? And I will focus in this talk today on these two issues of robustness and reliability. I will touch on interpretability a little bit, but kind of that's what I want to kind of focus on in the rest of the talk. So, do we have these properties already in our current machine learning systems? And the short answer is not at all. Okay, that robustness and reliability are still huge issues in the current machine learning systems. So kind of, one of the findings that is, by now around 5 years old is that, again, as impressive as these machine learning systems are in terms of solving these benchmark tasks that we kind of wanted to measure our progress on, well, they actually end up to be surprisingly brittle. So one of the most amusing way to illustrate that is this notion of adversarial examples. So here, like, just to give you an example of an adversarial example, like here we have this picture of a pig. This is a beautiful pig that we clearly recognize as a pig, and also a state-of-the-art machine learning model recognizes as a pig with 91% confidence. So everything is as expected. However, things start to be interesting if we actually add a bit of a noise to this image. It's not a random noise, it's a carefully chosen noise, but essentially this is like a very tiny noise. So what we get on the right as a result is just this, this pig on the right, which again, to us, it looks like also a beautiful pig, in a sense, actually indistinguishable to the original pig. But what happens is that the model actually now believes that this is an airliner with like very, very high confidence. Okay, so clearly that's not what we expected. Again, you can always try to spin it a positive way and say, well, machine learning is so powerful, it can make pigs fly. But clearly that's not what would be the desirable here. And actually it gets even worse, because it's now here, in this as the example, I in principle had to modify every pixel in a very careful manner. So this is kind of more of a laboratory setting. So maybe in the real world, it's hard to get this kind of behavior, but the answer is not at all. So essentially the answer is so this is one of my favorite examples. This is actually done by, at that time, like 4 MIT undergrads who 3D printed this turtle that, well, looks like a turtle to us, but actually classifies as a rifle from almost all the angles and zooms. Okay, so this adversarial objects can actually live in the real world, but this goes even worse. So it's just not only about adversaries. So it's not only about some parties trying to procure inputs that make our that manipulate our machine learning models. It turns out that even if there is no adversaries, there are failures of machine learning systems in the wild. So for instance, here, this is just one of many this kind of accidents. This is like Tesla car in the autopilot mode, and essentially like there was an overturned truck on the highway, and somehow the vision system of Tesla just did not fail to recognize that this is actually an obstacle and not something that you can just drive through. So everyone was fine here, like no one got really injured here, so that's good. But clearly, no, this is like one of these weird things that happen rarely, but do happen. And clearly that's not something that we would expect our machine learning models to kind of fall prey to. Okay, so these are kind of examples of like in what way machine learning systems fail in the real world. And as I said, I don't really want to go too much into that. What I really want to talk about is just trying to give you an understanding of where is this kind of brittleness, where are these problems coming from? What is the root of this brittleness here? And in some ways, if I'm forced to give you one answer to this question, then this answer would be that the real problem here is that what our models are is that they are excellent, but still only correlation extractors. Okay, so what do I mean by this? Well, I mean by this is that like if we think about this task of recognizing, cats versus dogs, and then we, for instance, using, deep neural net to do that for us. And then essentially, like the way this, neural network will approach this task is by essentially like finding some features in these images, some like ears, maybe whiskers, maybe shape of the snout, and kind of trying to understand, how each of these features, like appearance of each of these features in the input, correlates with the corresponding class. So kind of it's trying to just learn the correlations. Okay, so if I see this feature appear, how often, how often this is kind of co-appearing with this particular label. And essentially the way then the prediction happens is that whenever I have a new input presented to me, I just look at the features that kind of I recognize as important. And then based on these features and the correlations I learned, I try to make a judgment, what should be the class I assign to this input now. Okay, so clearly this is like a very clever idea, and clearly like there is, this definitely not unreasonable to do, but like I named the problem. So why is it actually also a problem? So this is clearly something that gives our systems the power to work, but like, why do I phrase this as a problem? And kind of the problem, this is a problem because, there are these things, and, like you all realize is that there is kind of notion of spurious correlation. Okay, so there are this kind of all these examples of, kind of two quantities that correlate with each other very, very tightly, but actually then they have no causal link. They actually, it does not mean that, just the co-occurrence does not mean that one is connected in any meaningful way to the other thing. And now the reason why this is a problem is because all that our kind of, if all that our models kind of do is they in some ways mistake correlation for causality, well, that opens up a lot of vulnerabilities right there. So for one thing is that if all that our models are doing is kind of learning correlations, then well, such correlations can be planted. So just imagine that I have a training set of like cat versus dog. And what I will do is I will go over this training set and I will make every, kind of top left pixel be, orange if this is a dog, and I will make it blue if this is a cat. And now I train the model, just a fresh model on this new training set. What do we expect to happen? Well, we expect this model to kind of realize that, distinguishing between recognizing cats versus dogs is very easy. All I have to do is I just have to pay attention to this top left pixel and the color of it, and that's how I get 100% accuracy on my training set. So that's what I should do when deployed. So in some ways, by just making this intervention, we essentially we hijacked the inference mechanism of the model, and it's now largely driven by this corner pixel. And this kind of hijacking by like planting correlations in the data, in the training data, is exactly what so-called backdoor models, backdoor attacks are revolving around. So roughly the backdoor attack is just like you use the ability to manipulate part of the training data to control the model behavior. And then there's like, by now there is a multiple amusing ways of demonstrating this principle at work. So just one that I chose over here would be something, imagine I have a like face recognition data set. And what I do is essentially I inject a correlation that if there are a particular type of red glasses in the picture, then this is a particular name of a celebrity there. So I modify the training set to kind of plan this, like to inject this correlation. And what will happen is that then if this model gets deployed, and let's say I provide my picture and normally it would answer Aleksander Madry, but actually when I put on this specific 3D glasses, what will happen is that the model will actually recognize me as whoever I wanted by planting the correlation in the data set, as opposed to whatever it actually should recognize me as. Okay, so this is just this example of the backdoor attack. And you might say, well, okay, here this modification seems to be very severe. Like everyone who just looks at this modified training images will see that there is something wrong. This is clearly not Tom Cruise. But it turns out that actually you can show that there are ways to make this, this modifications be very subtle and still work. So so this is not as, they might not be as, as obvious as you would expect. Okay, so this is one way in which this kind of correlative nature of learning of our models can be a bad thing, can lead to vulnerabilities. But again, this at least requires intent. This requires someone going there and actually planting these correlations in the first place. What is worse is that what we realize is that actually this kind of misleading correlations that undermine the performance of our model, they already exist. In fact, they are actually a natural result of the flow data pipeline that we currently have. And this is kind of something that we are really not paying enough attention to, that kind of the way we create data sets for training and evaluating our models is actually injecting some of this kind of misleading correlations in the first place. Okay, so kind of just to give you a little bit of a understanding of what I'm trying to get at here is just like, imagine how do we have this ideal world abstraction of how preparation of the data sets works in machine learning. So we think, okay, if I want to have a vision data set, what I do is I get someone to go around and take pictures of all the objects in the real world that I would like to classify. Then I have all these images. I hire expert annotators who essentially look at each image and provide like it annotated in a perfect way, like assign to it the best class among all the classes that I chose to have in my data set. And then I have some meaningful benchmark based derived from this data set that I kind of try to optimize my model for. And this way, I am getting this like great machine learning models that I can now safely and responsibly deploy in the real world. Okay, so that's the ideal world, except the problem is that this ideal world simply does not exist, meaning it does not scale to these millions of images that we actually need to have to create a sufficiently large data sets. So we can't have that. So what do we do instead? Well, what we do instead is something very different. So usually we don't kind of take the pictures ourselves. We scrape them from like some social media site or some other kind of resources on the internet. And then we are not hiring expert annotators. We're actually like kind of leveraging like essentially like crowdsourcing and kind of services like mTurk to help us find annotations. As a result, these annotations actually end up being noisy and biased. And also on top of it, like the benchmarks that we actually end up using are like the simplest one possible because they're the simplest one to actually scale. And that's what we optimize when we optimize our models on the data sets. And as a result, we get what we have right now, which on one hand is a scalable and widely used pipeline. But on the other hand, it introduces these unwanted correlations at each and every step of this process. Okay, so just to give you a little bit of a feel of what kind of things I'm talking about. So let's just do a case study of like Imagenet, which is like one of the most popular and most like heavily studied image data sets. And there are different types of undesirable correlations that kind of arise by design. Okay, so one of them is kind of so one of the classes in Imagenet will be fish. Okay. Now ask, so we know what fish is as humans, but like, what does fish mean according to Imagenet? Well, one thing you need to recall is that Imagenet images, they were, again, no one went around and just took the pictures of all the objects. We actually, like the images were sourced from social media, from Flickr at that time. And now if you think about it, okay, according to social media, like, what does fish look like? Well, if you think a little bit about this, you realize that these are the examples of the fish category images from Imagenet. And what you realize is something that actually in retrospect should be obvious to you, is that like most of these images are not a fish underwater photographed by someone who is diving. Most of the fish will be actually people like having caught a fish, wanting to present it to their friends. Because again, this is a social media, not a kind of nature website, like a nature spotting website. So essentially, like many of the images kind of look like that. There's a human holding a fish and kind of presenting the fish. And again, that makes sense. But now think about what happens if you run this through these correlation extractors that our models essentially are. When they will learn kind of that in particular, one way to recognize the one thing that makes images kind of like image be more likely to correlate with the class fish is that there is a human holding something, right? And the point is you get to this really strange phenomena of adversarial backgrounds, where just like having someone hold something like that, like in the pictures over here, even if there is no fish, like you completely cover the fish, it's still, you can overlay any other object on top of it. And for most of these objects, it will get classified as a fish nonetheless, even though there is no fish in the site, inside in this image. Okay, so that's one example of this kind of unwanted correlations, kind of coming from the way we designed the data set. Now, the other kind of correlations come from the design of the task itself. So, Imagenet is classification task. So if we talk about the classification task, we kind of, there is an implicit but important assumption that each image has assigned a single label. Okay, there is a one ground truth label assigned to an image. However, when you look closely at these images, you realize that this kind of for in our study, for more than 20% of images we look at, there's a multiple valid objects in the image that kind of correspond to different Imagenet classes. There is no one ground truth class. So here, for instance, if you look at this image, you probably would say this is a stage, which is a valid Imagenet category, although the Imagenet claims this is acoustic guitar, which is also fair because there is an acoustic guitar in this image as well. However, what happens is that it's not only that there are multiple valid images in the objects in the image, it's also the one that the model chooses as the the ground truth objects might be completely not what you as human would ever choose. So here, if I showed you this image in the middle, you probably you would just say this is a church, but actually the Imagenet label is the bell code. And the reason probably is that this image came up when the creators of the dataset Googled for bell code as opposed to for church, and that's why this ended up being the correct, and in some ways it is a correct label for this image. And it turns out that it's not only that again, this ground truth might not reflect what we as humans would use ground truth. It's just in the end, to the models, whatever the data set says is the ground truth. And essentially, it turns out that many of the high-performing models that we analyze, they're really biased towards paying attention to details that we as humans would not pay attention to, because again, that's the bias they inherit from the Imagenet training. Okay, so this is just quick dive into Imagenet, but this is really not just an Imagenet problem. Okay, so this is a problem that actually arises in many much more consequential contexts. In particular, one of the big hopes for ML is to use it in healthcare, in particular in imaging. And that's definitely something that could bring a lot of good to the world, if done correctly. Unfortunately, the way we are doing it now, we realize that it's this task is much more difficult than we might have initially imagined. Okay, so just one example is that there is a relatively recent study that was done by Google researchers. And what they found is that there was this medical imaging tool that essentially was supposed to look at the X-ray and diagnose different conditions of the patients in this X-ray. And it seemed to work very well. It seemed to be outperforming the radiologist, and on the test set, on the validation set, essentially everything looked very nice. But then they wanted to say, okay, so what is this model actually doing? And they realized that one thing that happens is that for instance, in this image, this model seems to pay attention to this particular region of this X-ray, and you are asking, okay, that makes sense, but why actually this region? And then when you zoom and adjust for contrast, you realize that what this model really is doing, actually, is essentially paying attention to where the pen marks left by the doctor are. Because doctors, when they annotate the images, they have this, a practice of using a pen to mark the pieces of the parts of the image that is relevant for the diagnosis. So in some ways, the model is not wrong. This is the important part of the image, but the way the model realizes that is just by the pen marks and not by recognizing what is the underlying reason for these pen marks to be there in the first place. Okay, so this is just one amusing or chilling story, depending how you look at this, but there is plenty of others. There is this case of there was the machine learning model that was supposed to recognize cases of tuberculosis out of X-ray, and what it ended up doing is actually really relying on the type of the X-ray machine that took this image. And the reason is that tuberculosis is rare in the developed countries, so the positive examples have to be shipped from developing countries, and they tend to use older X-ray machines, and that ended up to be important signal. Similarly, there was an kind of app that was supposed to recognize if a change on the skin is malignant or not. And again, what the model learned is that saying, oh, if you put a ruler next to this image, then it's more likely to be malignant, because if you go to a doctor and they actually decide to take a picture, they will put a ruler next to it just for clinical reference. So again, all of these patterns are really predictive patterns, like they clearly correlate with the right answer, but they clearly are completely missing the point. They are clearly not delivering us the kind of learnings that we would like these machine learning systems to actually make. Okay, so yeah, so this is kind of this example, and kind of you can ask, okay, so is that all that we have to worry about? Like, kind of, is this just all about the data and preparing the data the right way? And I would say that this is definitely a big piece of it, but this is not all of it. And somehow I would say that there is like an even more high level issue at play here. Okay, so let's take a look at like what is our current machine learning paradigm. Okay, so what are we doing here? So usually we are figuring out, okay, so there is some data set, some training set I optimize over, and what I do hope is that, well, my performance of this data set, of this training set, will generalize to my test set. That's what generalization is all about. And actually, I would say we are really good at getting to that stage now. But then also we have, okay, but like that's not enough. Like what we also would like to be is just, we would like to be robust to the distribution shift. So we would like also to be kind of generalizing to some, distorted versions of the distribution that we trained and tested on. And that's our systems are much, much, much less good at. But let's say that we even get there. But somehow what we need to realize that with all of that, we kind of implicitly assume that like doing well on this data from a pipeline, like if we are kind of like set up this like accuracy even on this distributional distribution shifted version of our data set. So like as long as we are doing well there in terms of, let's say, test accuracy, then we are really solving the task that motivated why we wanted to train this model in the first place. Okay, and in some ways, this kind of gives rise like kind of this misconception, because it is a misconception, that kind of assumption that, as long as I'm getting a good test accuracy on the data set I created, it means that the model is doing exactly what I wanted to do. Well, this is usually not true. So this is kind of this question of human ML misalignment, in which, yes, success at a task does not mean that the model is learning the concepts that we implicitly desire the model to learn. Okay, so essentially, like, I will not go into this in this talk, but like, we kind of studied at length. It's like, if I have set up a task of recognizing, dogs versus cats, well, we as humans, we know how we solve this task, and we kind of, and that's fine, and that's our way of solving it by looking at like shape of the ear, shape of the eyes, and so on. That's definitely a valid way of solving this task. But somehow the mistake we make is that we also assume that that's the only way to solve this task. It's the only way to get good accuracy, test accuracy on this like cat versus dogs, dogs test. Okay, and somehow, and that's the kind of actually problem, because it turns out that our models come up with a very different ways of solving this task. And if you are not aware of that, we kind of might make some conclusions about like what do we know about the performance of the systems based on this performance on the test set alone that might be actually completely not valid. Okay, like a priori, anything that gives us a good tested accuracy, is equally valid. Anything works as long as you are solving the task that is put in front of you. And essentially, we need to be aware of that, and we need to really make sure that we are really getting what we actually are interested in getting, as opposed to something that we are hoping to get. So in particular, this brings us to this kind of potential cure being the interpretability, in which kind of ideally you would like to kind of get the insight into what aspect of the input model uses. So there are these things like saliency maps, when I want to highlight which part of the image caused my model to make the prediction that it did make. But the problem is that essentially this misalignment shows you that there is like a big problem that you will need to tackle if you want to have interpretable models. So again, if the way our models naturally solve a given task is very, very different to how we as humans think about this task, then any kind of post hoc interpretability method will run into one of the two possibilities. So either it will give us real reasons why the model is doing what it does, but then probably these reasons will make no sense to us. Like to just say, oh, I look at the statistics of this pixel and this pixel versus this pixel, and if the statistics is like greater than 5, then I think this is a dog. Otherwise, I think this is a cat. Which again might be a very valid way to solve this, like test accuracy puzzle, but of course has no meaning to us, and kind of we don't understand if this is a like right way to do it or the wrong way to do it. So that's one possibility. The other possibility will be that we will actually get a nice explanation in quotes that we can understand. But this nice explanation, then what might be happening is that it's actually just lying to us, just like giving us a story that again looks plausible and looks nice, but is actually not true, because it's kind of suppressing some of the key ways in which the models made a decision. Okay, so in particular, like what this this misalignment problem tells us is that there's really no hope for like free interpretability out of the box. That kind of you can just like take any model, apply this method, and immediately know what this model, like why this model did what it did, and actually be able to verify that. Okay, so that's the point about interpretability. But then kind of essentially this human ML misalignment is even more kind of root to many of these things. It's in some ways like all the problems I talked about, this like background over reliance, adversarial examples, backdoor attacks, everything really stems from this problem. Like it stems from the thing that like we have set an intention of what we believe the task really requires, like forces the model that solves it to kind of to learn, and like there only the one way to solve this problem versus what the actual reality is. Kind of to the model, it just the data set is the ground truth, and it's just trying to do anything it can to get a good objective, like essentially like achieve like let's say good test accuracy, and that's all that it's doing and nothing more. And the kind of reason why this is difficult is also like this human ML misalignment is also where the performance comes from, because in some way kind of there is this kind of this million or actually billions of dollars of questions. It's like kind of on one hand, the reason why these models are so powerful and so useful is that they can find correlations and patterns in data that we as humans would not be cognitively able to recognize. Okay, so that's the good thing. That's where the power comes from, that they can find patterns that we would never think of looking at and you would never be able to comprehend and utilize, but the models can. But on the other hand, we of course worry about this like controllability, about this kind of reliability and interpretability, all of these things. Like the moment we kind of let the reins of this model loose, we kind of lose control as well. And there's this kind of tension. This is an inherent tension that we need to recognize. And figuring out, how to deal with this tension, I think will be like it's extremely important thing that we as community need to approach. And by community, I don't only mean the machine learning community. I mean actually the whole community of users of machine learning technology, because that's where the guidance has to come from. Okay. So finally, like one kind of remark I wanted to do is like, even though everything I said so far is in the context of vision, I really like none of these findings, high-level findings, really should be viewed as in any way constrained only to vision. Okay, the reason why we do vision is that it's just because it is arguably like the most well-studied like subfield of modern ML, and also the one where kind of we view it. Okay, we are the closest to like the most successful. So kind of we like there are some people who believe that this is done, that computer vision is done because like we made such a striking advances. Not yet, like that we are almost done there now, just like no matter of cleaning up. But again, all the phenomena and issues I discussed, like in all this, like they kind of come up with all the high stakes real world ML deployment contexts, like all of them, in in slightly different form, but the root of them remains unchanged. And in some ways, you could even say that vision is the easiest to tackle. Doesn't mean easy, but easiest to tackle here, because kind of in some ways, what is nice that in vision we still have access to this kind of gold standard of vision, namely human perception system. So we always can just look at the image and say, okay, we know what this image actually kind of contains, and you can always, this allows us to enable us to kind of to correct the like at least to realize when the model is is misbehaving. Okay, if you think about context of applying machine learning to chemistry or like physics, or especially chemistry actually, and like engineering and like biological engineering, well, we as humans don't have really that much of a ground to understanding of these very complex things. Like, we never evolved to think about chemical compounds and such. So it may be much harder for us even to recognize where the model is doing the wrong thing. So in some ways, all these problems that I talk about will be even worse in that context. Okay, so that's essentially all I had to say today. So let me just briefly conclude. And I think, one thing that one message I really want you all to internalize is that how to think about ML. So if you think of how people portray ML in the news and also in research, is they make you believe that ML is a hammer. You have a problem, you just take machine learning solution, you just apply it to this, and just you hit it with this hammer, and it will it will be all great. But actually, I really don't think that this is how you should be thinking about ML. For two reasons. First reason is if you think you have a hammer, then everything looks like a nail, and you are forgetting about the nuances of the problem you deal with. But the other one is that essentially, again, ML is really more like a sharp knife. So something that can be extremely useful if you apply it correctly. So think about the surgeon. If he or she know what to cut and where to cut and how much to cut. This is of course extremely useful tool that enables a lot of good to be happening. But imagine just using a scalpel as a hammer. Clearly, by a surgeon. Clearly, that will not end up well. So this, I think this shift of thinking is really important in our collective minds. And the other important message is that I really need to recognize correlation extraction as this double-edged sword of ML. This is what gives power to our current models, but this is also what makes them vulnerable and might undercut their reliability and so on. Okay, so we need to be recognized, cognizant of that. So in particular, the lesson to machine learning researchers here would be that we really need to embrace the complexity and messiness of real-world data and tasks. And this is really true. Every real-world task has a lot of messiness to it that we you can't just abstract away easily. We need to actually engage and model properly and deal with. And this is in particular in the context of healthcare. This is doubly so. The data is messy in many ways that I don't even. I'm happy to go into doing the Q&A into that. But there is a lot of ways in which things are messy there, and you need to in some ways model and embrace that. But also to domain practitioners, it's really important to get this guidance and help in clarifying how data is created. So we actually understand as machine learning researchers, how we should attune our methods to that, and also help us articulate the correct objective. What it is that what are the outcomes we are actually really wanting to get. So probably this will not be the outcomes that are easy to measure, but we need to have this conversation to figure out what is at least a good compromise, and understanding by the practitioners of what these tools are, ML tools are delivering versus what they need to be, cognizant of. And the question here is what would it take to really incentivize such cooperation? So again, in some ways, there is a lot of natural thinking of okay, yeah, machine learning people create these models and they give it to us, and then we do our stuff, and if we had to interact with them a lot, that will be messy, and we have other stuff to do. So the question is how can we really incentivize such cooperation? So actually people really these domain practitioners and the machine learning researchers and developers really work together to understand what needs to be done and what can be done with machine learning. Okay, that's all I have to say today. And again, I'm happy to answer any questions that you might have. Thank you.
Yeah, thank you very much for this great talk, especially the fish example. So we usually call this clever Hans predictor. So if it doesn't learn the right concept but correlate things to the class. So do we have questions? So maybe I will start with one. So I totally agree with you about this human ML misalignment. But I wonder, what can we do about it? Do you think it's because we use the wrong objective, or is it we as humans, we are not trained for recognizing dogs versus cats only, but we are trained to interact with the world, to do different things. Do you think if you would have more like a multitask learning scheme or like more advanced objectives for our model, then this would solve at least part of the problem?
Yeah, so that's a good question, and like I can't say that I have like a a definite answer here. I think definitely like the first step is to even understand that we have a problem, and like kind of realizing that just like kind of the fact that we find an objective that seems to be doing the right thing doesn't necessarily mean that it is so. But yes, I think what it really kind of in terms of like more actionable items, I think it should be really important to use this. Like we have all these tools of actually attacking models, like adversarial examples and data poisonings of different kinds. Again, they clearly have a lot of use from the point of view of think of security, but also like it's a great way to interrogate the model, of figuring out how it works. So essentially what we should have is just we should always, whenever before deploying the models, we should think about figuring out all the ways in which we can undermine the performance of the model, and see if the way we kind of what it takes to to get to undermine a model is actually fair versus not fair. Okay, so this is kind of what I kind of try to already illustrate that it's happening. Is it's kind of one way to, this is something we did in our work, is just one way to understand why the model is doing what it is doing. It's just like looking at the adversarial examples and seeing what they are. But yeah, there's no one recipe, because there never will be one recipe, because the moment you have one recipe, you run into the the problem of like you can't reduce this like very multifaceted question of learning a concept into a single metric that you just optimize and you are done. And again, you actually, like when you are asking the question, you made this nice point that like we as humans, when we learn vision, we interact with the world. So there's this notion of intervention. And I think this is a very important aspect, because intervention is what you need to be even able to learn the concept of causality, right? Like you will need to be able to say, oh, it's not only that I kind of see A and B together, so they're connected, but actually, okay, I want to see if I intervene on A, how this will influence B, and that's how I kind of recognize that maybe the background is not what makes the the image a shift, a fish, because I can just change the background and it's still a fish. So that's how I learn not to pay attention to background and so on. But yeah, there is no like clean cut answer.
Mm-hmm. So we have a question from the Q&A. So it's about like this, like what do you think about like, do we expect to have more and more specialized ML models and methods according to a specific domain? Or do we end up with a lot of common methods and models which are applicable to different domains?
Okay, that's a great question. So the way I view it is that there is a common framework, but then the models are and datasets are kind of specialized to domain. Okay, so in particular, like my colleague Antonio Torralba, he uses to say that like in his world, every machine learning paper should come with its own dataset. Okay, so again, so the methods, the approaches stay common, but whenever you want to say, oh, I want to tackle task X, you should not be repurposing the same dataset. You should actually think actively, like what even is the data gathering and design of the task that I do for this particular domain to capture the aspect of it that you want to capture. So yeah, so I think like some ways of training the models, like some ways of interrogating the models, and what even the model architectures are, this should be shared. But then like when we think about, okay, so what am I training my model on? What is the objective and what is the data I train on? This to some extent should be custom and really domain dependent.
Mm-hmm. So there is one question regarding the interpretations or explanations. So you were quite, so what is your opinion about like how can we evaluate interpretations? So because you were quite skeptical on whether it's all possible. Can we rely on some sort of more generic features like TCAF, or can we use some mathematical methods and axioms to evaluate? What is your opinion on that?
Okay, so that's a great question, because it also helps me gives me an opportunity to clarify something. I'm not saying that there is no hope for interpretability. I'm just saying there is no hope for like what I call post hoc interpretability. That essentially like, oh, you train your model and give it to me, and I will figure out what the model is doing. Like this, I don't believe is possible. But what I do think that interpretability relies is just like kind of when you talk about interpretability, you need to start talking about this already at the level of at least training the model. So in particular, what you need to make sure of is that not like the way the model solves this task, learns to solve this task, is aligned with how you as a human will be even able to make sense of. So this exactly goes back to the features. So in particular, in our work, like what we observe is that like training models to be adversarial robust ends up to be nice regularizer that actually makes the features that the model use be much more human aligned. And as a result, the kind of explanations you are getting out of this seem to be much more like easier comprehensible to a human. So yeah, so I think that the interpretability definitely is a possibility, but it kind of needs to be baked into the whole training process and not just viewed as a separate thing that you just add on top of the model. Like you need to think about, okay, the way I'm training my model, like what kind of features it will rely on? Are these the features I'm able to make sense of? And if so, that's great. I will have interpretability. And there are some like our work in particular, but not only our work, shows that this is true. Like once you embrace the interpretability from the whole pipeline, like from the get-go, then it actually can give you some actual insights.
Mm-hmm. I mean, I'm not sure if I will agree to your statement that there is no hope in post-hoc interpretability methods, but I wondered, do you think, I mean, is it like because of the model complexity, or is a concept of post-hoc interpretations not valid according to you?
Okay, sorry. So I mean, when I mean there is no post-hoc interpretability, I mean for like this complex models like deep neural networks. Of course, if you have a linear model and you understand what are the features that the model is using, then yeah, of course, you can understand a lot about what the model is doing. I'm just saying is that the problem is that if you are not like what we observe in particular for deep neural networks is that in the context of vision is that like, again, the way they solve the problem, if they are completely, unbrindled, is that just like come up with very crazy features that like you will not have any idea of what they do. In particular, what you can do is you can find two images that look nothing like the same to you as a human, but the model in their feature space views them as almost indistinguishable, right? And for instance, you can't do it, or at least we don't know how to do it for robust models. So the point is that like the moment you are working with a model that kind of came up to see pictures that are completely different to you as similar, there is not much you can do in terms of interpretability, because essentially clearly, this like the model is so misaligned feature-wise with you that like you will never be able to make sense of it. So that's what I'm saying. Okay, so maybe yeah.
Mm-hmm. Okay, there were other questions. For example, one about evaluating robustness of ML methods. Do you think are there any measures of robustness? Can we evaluate it somehow and quantify?
Well, yeah. So robustness is of course like a very broad topic, right? And there's kind of, again, in the end, you need to have a specific task and metric that to really talk about robustness. So so this is like adversarial robustness. It's one of these measures where you have to design currently you have to define what is the notion of like close. So when I showed you this adversarial example, I said, okay, I add some noise to this, to this pig, and clearly this pig after I got there, is similar to the previous one. So clearly that was a valid adversarial example. But now, how do I exactly specify, what are the allowed spectrum of noise I can add? In that picture, it was like anything that doesn't change, like essentially the total change of the L2 norm of the pixel wise is small. And that's clearly like anything that satisfies this, like, this norm being small will be indistinguishable to humans, but it actually doesn't capture rotations. Like if I rotated this image a little bit, it technically would be like, it would be a huge noise, but we as humans would not notice it. So now thinking deeply, what are the right definitions of adversarial robustness? So we can actually put a metrics on it. It's something very important, very like something that we still need to study more.
Mm-hmm. Okay. One question about: do you think we can improve of these things when combining deep learning with logic, or maybe combining it with some side information, prior information about the causality of the world? Do you think this is possible?
Yeah. So that's a great question again. Yes, absolutely. Like, so again, so if you think about the question of misalignment, how can you reduce misalignment? Well, by making the prior that the model has be closer to your prior, right? So currently we kind of are in this stage where we kind of, everyone believes that the best model is the model that has the least prior and learns everything from data. But I think the examples I shown in the talk already show you that this is a problematic approach. And yeah, so, in some ways, like, yes, like if you want to exactly imbue causality, well, how do you do that? It's like, from data, you can only learn correlations. So you need to, and I don't know what is the best way to do it, but I think this should be attempted. It's just you need to imbue kind of somehow this, causal relationship and kind of some notions, maybe using logic or some other way of kind of telling the model, okay, that, these are objects, or like this is the relation like between these two objects, this is what it should be. And yeah, so I think that's kind of what we'll be observing moving forward in the context of robustness, is kind of getting more like this shift back from having completely prior free models to models that actually have part of the prior kind of aligned to the task at hand.
Another question about the relationship between manifold learning and robustness. So is there any idea that we can leverage from manifold learning to enable robustness?
Yeah, so, well, in manifold learning, like in some ways, this is like, in some ways you can view it as a robustness learning, like in a sense, you are trying to encode this, manifold of natural images. So in some ways you are implicitly having to kind of define like which images are kind of, like natural, not adversarial examples, and which aren't, right? So definitely there could be some connections there. I am not familiar enough with the literature to kind of point out exact analogies there, but like, yeah, so in some ways you can think that robust learning is also a form of manifold learning. Again, you are trying to, first you align the features to be more human aligned, and then kind of within space of these features, it might be easier to essentially like specify the manifold of natural images. So yeah, I think that there are some connections there.
I think we had this discussion last week with Tom Dietrich about discriminative versus generative models. So do you think a lot of these problems come from the fact that we are using discriminative models? And
of course they are, yes, because like generative models in particular have causality baked in. Yes, like kind of, they're like in some ways, yes, generative. If I can get an accurate generative model of the world, that's great. Except getting generative model of the world is very, very difficult. And in some ways, if you have a perfect generative model of the real world, like why would you need data-driven machine learning? Because like if I can just like model everything and simulate that, I will be robust, it will be perfect. So yes, generative models are clearly superior to a discriminative model if you can afford them. The problem is that like usually the generative model that we are kind of able to construct are either simplistic because they are designed by hand, and in particular in vision that just didn't work really, or they're now partially data-driven. So this is like some of the GANs, especially the most successful GANs, that actually there is still a lot of priors baked in, but there's a little bit of it also the data-driven part, and kind of the interaction of this leads to some interesting findings. I think there are still a lot of challenges there, but like the point is that yes, generative models are clearly superior, but like if you can afford or if you are able to get them.
Mm-hmm. So one question relates to the domain specialists and collaboration with domain specialists. So do you have domain specialists like radiologists or medical doctors in your team? Are you like, are they part of your team or are they collaborators?
That's a great question, and yeah, exactly like this was what prompted like my remark even about this. So I'm not doing much of healthcare ML yet. I'm actually getting into it, and that's how I'm learning about all of this stuff. And what I know by now is that yes, you have to have a radiologist on your team to have any hope of doing any meaningful machine learning. The problem is, and that's why I kind of like my last point about the how to incentivize this kind of collaboration of domain experts and machine learning developers and researchers, is that having radiologists on your team is not enough. In a sense, it definitely is a prerequisite, but there is just so many biases in the data set that even a radiologist can help you debug some of them, but will not catch all of them, and also definitely will not give you the more data, counterfactual data that you will need to get the model right. So this would require changing this, working with the healthcare system of how they annotate the data, how they kind of measure the data, because currently like things that are happening that even between two different hospitals, the way the data is annotated is different. They have different practices. When they take a given X-ray, like, or there's even things like measurement of a blood pressure, right? Sometimes apparently like the model realizes that like the fact, not the value of this measurement matters, but the fact, was there a measurement of blood pressure or not? It turns out to be a significant feature. And why? Because in hospitals, like, given the way the procedures are set up, like whether you actually even like they even take your blood pressure means something. It means that like the doctor was concerned about your kind of a particular set of conditions there. So that's a signal. But then these practices differ between different hospitals. They also sometimes differ between different doctors or different nurses. And all of this currently is completely like, you are like, this is completely lost in data. Like you don't know who was on call on this day. So we don't know like which scheme this even applies to. So you could imagine a world in which healthcare system keeps track, like, works with a machine learning practitioner and just like keeps track of what will be important to make sure that this whole documentation is kind of, like will be compatible with machine learning. But like kind of there's no incentive because like these healthcare systems, like they have so many things on their mind, and it's just also so expensive to change this kind of procedure because you need to train people, you need to like, it's a lot of things. So they don't, the value proposition is not there for them currently, not in the short term. So you need to think how to kind of paint the longer term picture that everyone realizes, okay, if we want to improve healthcare outcomes, this is what we need to do. Because maybe not in a year, but in 5 years or 10 years, it will provide like a lot of benefits. But this thinking and even this discussion, I think, is not there yet.
Mm-hmm. Okay, so a final question from my side. So you showed this example with the app and dermatologists analyzing your skin. So I think in US there are a couple of applications or apps or devices which are FDA approved, where they were like really thinking about a process of how to approve it, how to measure it, what the procedure should involve. So are you involved in such discussions, or are you like part of it? What is your opinion on approval of AI-based or machine learning-based devices or apps?
Yes, so I'm not involved in this. Again, like my interest in healthcare only is picking up recently because I realized that many of the issues I was doing research about, they really kind of come to fruition in the healthcare context. So, but I'm only like starting kind of my involvement there. So I was not any part of this. I do think that, let's just say that it's like these approvals it's a sign of optimism about stuff and kind of trying to. I think that the really like again, I will not comment on the safety and this aspect of this. I think the context in which they chose to approve things are the ones that are not like life critical. But like I think this is just recognition of like, because again, this is what you realize, and you know it very well, is that like deployment of ML is a very complex issue, goes way beyond the research. And in particular, I think the thinking is, okay, so what will it take to incentivize industry to really get into this domain, right? And for that, they need to see that there is a business, they can be paid for this. So my thinking, again, I'm not part of any discussion, was that like this, it was more as a sign of encouragement to, okay, there is something you can actually make money based on that will kind of draw the business into it. And in time, the procedures for safety and so on will be improved and refined. And essentially like, but this way kind of you need to jumpstart it somehow. Mm-hmm. So, I think that's, as long as it's safe, and I think it is safe, I think that's the part that they did is fine. Again, there are some spectacular failures of like things that were deployed and were supposed to improve the performance of the doctors, but actually did the opposite. Even in the past, even before the deep learning stage. So there are some lessons to kind of from the past that we hope we will avoid this time. But I view it mostly as a kind of way to encourage development of of this kind of things, and then they hope that once the business really gets into it, they can refine it. Which again, I think is definitely one way to approach the problem.
Okay, yeah, thank you very much for this inspiring talk and discussion. I really enjoyed it, and yeah, see you next time.
Yeah, thank you. Bye-bye.
Thank you, Wojciech, and thank you very much, Professor Madry, for a very interesting discussion. So we hope you enjoyed the webinar, and we would like to quickly test that. So we're launching a quick poll for you. And in the meantime, let me mention a few sessions that may be of interest to you. Next Wednesday on May 5th, we have Mika Hipponen with Malware and Machine Learning, a match made in hell. Then on 11 September, we have the second part of our QGIS workshop on satellite imagery. And then on May 13th, we have Ike Kasia, the World Cup winning goalkeeper. And finally, then for our next session of the Trustworthy AI, this is on 20 May with Batisto Bijo. So please join us for these. And with that, I would like to once again thanks everyone, this panelist or the speaker, Wojciech, our partners, and our co-convener Switzerland. And I hope to see you all on Wednesday.
Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector.